trying to get these lectures up for you guys, but it's freaking out. All right, so this is the example we've been working on. If you pull up that chapter 9.r script, oops, wrong window. I have the data in here, and then what we had done to get standard deviation and standard error. Zoom in a little bit more. So be sure you rerun all the lines. So I have to have the data in my environment window or nothing's going to happen. So my summary of the data. Okay. So the mean is 28 minutes. There were 10 people. So that makes degrees of freedom 9, or 10 response times. I know there's 10 because there's 1 to 10 right here. And we were going to compare that to a 30-minute response time. Okay. And that's from the example, this thing. So our standard deviation's 3.71. And our standard error, 1.17. And then remember, this line was just me proving that this code did what we thought it did. So you'll get approximately the same thing, just some slight rounding differences. Okay, so where we were headed was how to finish out. We were here. Yes. Okay. So we're going to move on to step 4, and we'll do another example. So you have plenty of examples of this. So we're going to use our degrees of freedom to find our cutoff score, because we talked a lot about how the number of people changes the spread of the distribution, where less people is more spread out, so you have a further finish line, because the tails are fatter. More people, the tails squish in, that's the central limit theorem, and you have a closer finish line. So the more people you have, think about it as you have more confidence in your answer, and the more confidence you have, the less far you have to go. So we're going to use that Q function again. We were using Q norm, because we're using a normal distribution. We've switched to T. So now we're using QT. Right. But remember, and this is what a lot of people were, I haven't even looked at the test. I'm sorry. It was a long weekend. It involved a shower and a drain pipe. It's the wrong length. Lots of trips and loads. Remember, for a two-tailed test, this alpha is going to be divided by 2 because you need both tails. But we're doing a one-tailed test. So we're going to use QT. We're going to use 0.05 because that's what the problem says to do. But this one has a second number. So a Z, there's no worry about the number of people. But this does need to know the number of people. So degrees of freedom here. So that's n minus 1. So 9. And then the lower tail thing. In our case, we're doing a less than test. So lower tail is going to be true. So this number should be negative. If you have a less than test here, it should be negative over here. So let's try it. So I got a negative 1.83. So when we're calculating t, so it's going to be a little flatter than normal. We got a negative 0.83 out here. So this is reject. This is fail to reject. Because if the response times had gone up, that wouldn't be good, but it wouldn't support our hypothesis that she wanted them to go down. So we're kind of ignoring the fact that if they went up. So does this number make sense? Well, 1.64 is the cutoff for z-test, negative, for a one-tailed test. And this is a little further out. It's a little further out because there's less people than what you would expect for z. So with t, the closer you get to 100 people, the closer it gets to 1.64. So if I tried QT here, and if I had 100 people, that would make degrees of freedom 99, because it's n minus 1. So if we manage to find 100 of these times, it's 1.66. is much closer to the original z cutoff. We're like 1.64, what is she talking about? I can do the same thing. Q norm, 0.05. Right, there's no degrees of freedom. It's 1.64. So about 100 people, T and Z are approximately the same. We only have 9 though, so we got 1.83. I'd say the trickiest part of this is don't forget the degrees of freedom, because we haven't done that. That's new. So if you type QT 0.05 lower tail equals true, it'll tell you argument DF is missing. That's actually probably one of the clearest errors. Right? You're forgetting something. There are very few, I think, in this program. I was telling a student, they're like, when do you know you're going to get it? I was like, when you understand what the errors mean without having to Google it. So, don't know that I'm quite there yet either. What was it saying? So, it'll tell you, it'll warn you, P.S. you need another number. And they do need to be in this order. So, P, D, F, lower tail. On a table, I find the tables very confusing. This is probably the least confusing of them, especially because if you Google table, you get 6 different versions of it. But if you're looking at a table, it gives you the degrees of freedom. It tells you is it a 1-tail test or 2-tail test, and then it has 0.10, 0.5, 0.01. The nice thing about using R is I don't have to lug around this table. And I could pick P equals 0.0785812. I mean, you could pick a value that isn't on a table. But this is the important part from the slide. So which one's more conservative? So you might want to highlight the word conservative because I don't think we've used it before. 1-tail test or 2-tail test. So conservative is the opposite of power. So things that are powerful are less conservative. Things that are conservative. So like power and conservative is sort of like politics in a sense. They're opposite ends. So if a test is conservative, you are less likely to find the result you're looking for. Okay. So 2-tail tests are more conservative, so less type 1 error, which means they have less power. Yeah.
So this is from terminology. So that negative 1.83, that would be our cutoff T score, not our cutoff Z score, right?
Right.
Yeah.
Yes. This is all in T this time.
Yep. Okay, so no Z's.
No, not in this test. T and F. Okay. So a 2-tail test is more conservative is the answer. Because you're splitting it in half, so you have further to go. Okay, so they have less power. And that's actually from the power section. We talked about 1-tail test versus 2-tail test. 1-tail has more power, 2-tail has less power, so it's more conservative. It's just a new term. All right, so this is T critical, or T cutoff, however, whatever way makes the most sense to you to think about it. T actual, T found, T experiment. So it's mean minus mu, and this goes back to that table that we had from Friday, divided by standard error. The book is going to have it as SM. We've been talking about it as SE. Either way, it's the same formula. So I just kind of did this by hand. I would do 28 minus 30 divided by 1.17. 2 over 1.17. You guys know I'm not good at math. Negative 1.71. Close, but we would fail to reject, or do not reject. Because we didn't quite cross the finish line. So we got we needed 1.83, and we got 1.71. Now, if we have the number. So if you're given a problem that already has mean, mu, SD, all that calculated for you, you can just sort of fill in the formulas. So that's pretty common in the book questions. If you have the raw numbers, like we do right now, we can use ttest. So there's sort of two paths to the way these questions get answered. Either have the numbers, and I'll show you how to type it in, or you have the raw numbers and you have to calculate. So I'm going to teach you both. We're going to do ttest. It looks like a lot. It's not really too much. And then the scary code that's online, I'll explain that today too. So ttest is a base R function, so no packages. And we'll have to enter each of these things. So I'm going to do is t.test. And as you start typing it, normally it will show you, oh, very helpful code there. This is x, comma, dot, dot, dot. So that's not very useful. But first thing you want to put in is the name of where the data is. So we called ours data. I'm going to hit enter after each comma. You do not have to do that. I just like this stacked code because it's much easier for me to read. If you want to make it one big, huge line, that's fine too. The word mu, don't change anything on this side. Okay, so mu equals, and then pick a number. So mu equals 30 in this example. Right, so that's from here. So mu. Alternative equals. Okay, and by alternative, what they mean is what's the research hypothesis. So your options are less, greater, or two-tailed, I think. Hold on, I wrote them down. Like this. So less, greater, or two-tailed. Don't put all three of them in there. You could, actually. It'll run 3 tests, but you don't want to do that. Pick one based on step 2. And they do 2, it's 2 dot-tailed. So make sure you copy them the way they look here. We're going to go less. Oops. Sorry, I'm bad at this. Comma. And then conf.level. And what conf.level does is it tells me what the confidence interval should be. If you have p equals 0.05 in step 4, conf level should be 95%. If you have p less than 0.01, it should be 99%. It is the default, I think, is 95. But if you have p less than 0.01 and you're trying to get the confidence interval, don't enter the wrong one. So I think the alternative default is also two-tailed. So we're entering these to make sure that you know that you've got it matched to your exact question. So it actually will run with only the first 2 pieces. So we're going to go 0.95. Okay, so it's 1 minus alpha, so or 0.05 here. And then run all of those lines. If you put it all in one line, just run that one. So you should get this, and I'm going to blow it up. All right, so it tells me what t is, 1.70, because it did more decimals than I did. It tells me degrees of freedom, in case you weren't sure. Yeah?
Oh, I keep getting error that the object of less is not. Okay,
Oh, it's getting close. The word less.
I keep getting a different.
What? Why?
I don't know why you're actually.
Oh, you don't have data yet.
Okay.
So the code from online had data, but if you go back to your
Yes.
copy that. It doesn't have the data in there. Or it doesn't know what to do. Is that all the errors? No?
Yeah.
Okay, hold on, let me pause this. Okay, so where's that? Oh, so we got t, we got degrees of freedom, and here's something new. This p-value. This is found p. We're talking about, you gotta think of step 4 as alpha. So what is my critical p? That's the actual p. So for 1.71 or 1.70 in this example, p-value is 0.06. So if you aren't sure about this whole step 6 thing, 1.83 we didn't reject, B's 0.06. We want it to be 0.05. There's actually two ways to approach this. So when we did Z, we did the like percentiles and stuff. That is telling me the percentile. So it's in the 6th percentile, we need to be in the 5th percentile or less. So that should match. So if you fail to reject the null based on the cutoff scores, the p-value should have the same effect. So this is like, for step 4, instead of calculating the critical value, we could calculate the p found. You can do it either way. It does give me a confidence interval, but it looks funny, right? With this negative infinity thing. On a one-tailed test, it will calculate a one-tailed confidence interval. We've talked a lot about how most people do two-tailed confidence intervals, so that's not totally a useful number. But you can cheat, because I know everybody loves confidence intervals. So this is the actual test I wanted. But I could change the whole thing to 2.tail. 2.tail or tailed? Tailed ed. So the first one's my real test. The second one's just for confidence intervals. 2.sided. Oh, sorry. The code is incorrect. I looked that up online. Oh, I had it wrong. Sorry about that. I will update the notes. Okay, 2.sided. My bad. I'll do 2.sided. It'll still give me the same T and DF. The P will be wrong. Because two-tailed tests are going to have a different P because it's going to be doubled because there's two tails. But it does give you the confidence interval right there. Bam! No math. Woo! It's the same math as Z. The sample mean, still your point estimate, plus and minus T critical times standard error. It's the same formula, but thankfully we're going to have not one but two different ways to calculate it without thinking. Okay. So 2.sided will allow you to get the confidence interval, a two-tailed confidence interval. So to finalize this, step 6 is reject or don't reject. We already said don't reject. We actually just calculated the confidence interval. We've got the mean is 28 minutes. So the lower level or limit and the upper limit. God, I'm burning up. All right, let's see. 25.34. And then right here, 30.66. It's about plus and minus 2 minutes, 2-3 minutes. Does that include the population mean? Yep. So that's why we didn't reject the null. Okay. So it includes 30. 30 is our population mean. We wouldn't reject one-tailed, two-tailed, either way. Okay. Let's see. And then last but not least, we're going to do effect size, and I will show you what that scary code is. You will actually hopefully like the scary code. Effect size is still just got a different denominator. So with Z, the effect size is mean minus mu over sigma. E is mean minus mu over standard deviation. If T and D are the same and they're not 0, you've done something wrong. Okay. So T found and D should be different. D should be smaller because it has a different denominator. That's the only difference. So I got 28 minus 30 divided by 3.71. Okay, pull 3.71 from over here. So one of the reasons why we write down all these numbers here, other than when you write up things you need them, is that they've all been used. So mean, mu have been used twice. Standard deviations for Cohen's D, standard errors for step 5, degrees of freedom is for step 4. So they all get used at some point. Oh, wait, what am I doing? Click on the wrong thing. So I've got 28 minus 30 divided by 3.71. Negative 0.54. saying medium effect size. Those sizes are 0.2, 0.5, 0.8. That hasn't changed. The negative just means that the scores are lower. But while we did reject the null, it's a pretty big effect. So lowering the time 2 minutes is actually probably a good thing, although not significant. Okay, so this is going to cover a little bit of what we already did in R, but we are going to use two-tailed confidence intervals. Wow. You can do one-tailed confidence intervals, but they're really not very common. They're calculated the same way as Z, but T critical instead of Z critical. So you'll actually get the formula, but using the code function is much faster. But it's the mean minus T critical times standard error. Okay, but that's a two-tailed T. In this case, we only have one tail. So we would have to recalculate a two-tailed T. Upper is plus. The much faster way is to use ttest. And then, so to interpret this confidence interval, it's the same thing as before. It's just kind of a reminder, going back over some things that I think were kind of hard from the last test. So we were to sample in students, or 10 more response times from this example, over and over and over again. The 95% confidence interval would include that population mean 95% of the time. So 95% of the time, it would include the true population mean, which we're assuming is 30. And then informally, we talked about this, like how confident can I be in my sample? So really, why confidence intervals are a bad thing. Really small confidence intervals give you more confidence that you're getting an accurate representation of the population. So we want to be more confident, and that's a smaller interval. All right, so the scary code that's online. It's kind of a cheat. This is the more practical way when you have the calculated numbers. So let's say in the problem they only gave you this, and they didn't give you the raw numbers. Okay. You could plug and chug through all these different formulas, but once we hit independent T, that's going to be a miserable existence. So these are pretty easy little formulas, yeah. Once you get to independent T, you're going to be like, no, I don't want to. Okay. So I'm going to show you how to do this now, and we'll go over it again more. Okay. You don't have to do it this way, but it is definitely much easier. Okay. And the fun part is just getting over the way the code looks. Okay. So I posted both of these online. One's called fsize, one's called calculate. Okay. So you want to open both of those. The fsize one is the scary looking one. Yes. So it's under notes on chapter 9. Two options here. If you put all of your stuff in the same folder, sometimes this source thing will work. It probably won't today. Oh, of course it will. So it did today. But if the source link on the calculate one does not work, what you can do is come over here to fsize and tell it to run all. So highlight everything and run it. Okay. Don't run it one line at a time because it's like 600 lines. Yeah. But if you highlight everything, hit Control Enter, Control R, Command Enter if you're on a Mac. It might take a minute, but it'll run everything. If you have problems, give me 2 seconds. You know you've gotten it run when you suddenly see all these different functions. So this is the way you know it went okay. And I will pause this. Once you get all of this stuff over here, in the calculate one, so basically the only reason you open fsize is to just get all of these functions. You don't really want to look at them. It's very scary. Under the source one, it has like a bunch of explanations of what all the different symbols mean. But we're going to scroll down to where it says single sample T from means. Here. So this section is single sample T from means. And it's just got an example already typed in where you can just change the numbers to ones that you have. So those numbers are just there so that it will run. So what we do is M is the population mean, or sample mean, M. So we change that to 28. U here is for mu, that's the population mean, that's 30. SD we calculated as 3.71. Okay, there's no spot for standard error because this works with assuming you don't have standard error. N is 10. A out here is for alpha, and I'll write all this down in just a second. So I'm going to go 0.05. K is for the number of decimals you want to see. So I would just, the default's 2, I would set it at 2. And then if you run that, you should hopefully get, sometimes you might get a warning. Ignore it. But you should get this. So what do I got? I got my sample mean. I just repeated it. Standard deviation. Calculated standard error for me. So take standard deviation, divide by square root of n. Give me my 95% confidence interval, so it should match the one we have. It does. There's some slight rounding. They give me t with degrees of freedom, 9. They give me my p-value for a two-tailed test. So this always gives you two-tailed, because I don't want to F with one tail. Here's D right here, and this is actually the confidence interval for D. You can ignore that. So if you're wanting to calculate everything that you might need for one of these problems from the raw numbers, this is really easy. Once you get it like all the stupid code load. Okay. So it's mean, standard error, confidence interval, and D and T right here. This is written in APA style. My graduate students have never been so happy in their lives. I was like, yeah, and it spits it out in APA style. They're like, what? They were so excited. I have a little video on how to work this script too. If like when we get closer to the test, you're like, I don't remember any of that. You can watch the script and it explains like each piece one at a time again. Okay. But let me write it down real quick.
So you should save the f-size R file in the same one as the calculated to source store.
Yes.
Probably.
Sometimes source doesn't work because you have to set a working directory, but I don't want to even mess with that with you guys because you would all kill me. So if you try source and it gives you an error, just open f-size and run the entire thing. Okay. Alright, so mean, sample mean, sample man, U is the pop mean, SD is the standard deviation, N is N, I feel like that's pretty clear. What am I missing? Alpha, A equals so 0.5 or 0.1, K equals the number of decimals. If you leave off K, it just gives you 2 all the time. Okay, so that's the end of those notes. Don't save. Let's try the second one here. Just a little quicker. Leave those two up there, they don't change. Okay, so for the second example, the book examples are so cheesy. But, so college seniors report falling in love an average of 2.2 times. So I didn't even know this sort of thing. It took 5 people. 5 is way too small of a sample. But let's say they just took 5 people who were originally from this particular country, but instead have moved to the U.S. How many times did they fall in love? So did the U.S. change them, is I guess the question. They give us the numbers here. We're going to use p less than 0.01 this time. So Students who end up in the U.S. fall in love more often, so this is a greater than test. So is the DV scale? I guess you could say none. So it has a 0. I would say it's ratio. Can I randomly select? Not really. I can't really randomly assign either, because these are students who went to the U.S., so I can't just be like randomly like, you're going to the U.S. So probably not assign either. Is it normal? Oh wait, no way. N is way less than 30, it's 5. It's sort of hard to have a normal distribution at 5 people. Especially if it's bimodal. It's 2, 2, 3, 5, 5, so it's a bimodal distribution. So the DV is our falling in love. So the IV is students that are either spending time in the US or at home. So that sample is people who've gone to the US versus their normal population. So a normal falling in loveness for their country. I don't know that I think of the US as particularly romantic, but they seem to think it's going to be more often. So more often is greater than. So the null is going to be less than or equal to, because they've got to be opposites. So we're going to do a one-tail test again. So we need to calculate the mean, standard deviation, standard error, N for degrees of freedom, and they told us mu was 2.2. Over here for step 4, we're going to use p less than 0.01 this time. So qt 0.01, still 0.01, not divided by 2 because it's a one-tail test. So this is still one tail. Degrees of freedom is, we've got what, 5 people? So df is 4. And our lower tail equals false this time, because we want upper. Whoa, scary stuff. First thing I gotta do is type in the data. So I can call this data or data 2 if you want. C function for concatenate. Okay, let me move this up so it's not at the bottom for you. There you go. And I'm just going to take these scores and cut and paste them. Over here. 2, 3, 5, 5, 2. I don't have to be in order. So I've got the second data set. And so I really need my mean. So remember the function, we can use the summary function for that. So the mean is 3.4. It's looking higher. It's not going to be significantly higher. I don't know, we only have 5 people. The standard deviation, so SD, data 2. 1.52. Haven't lost anybody, have I? Still with me? Remember the crazy standard error formula. Okay, so I'm going to take my standard deviation, divide by the, so SQRT, so square root of n. So if you just want to type 5 here, you're good. Or we could do of the length of data 2. And make it calculate that it has 5 people. So be sure you leave in the square root part. Remember, it's standard deviation divided by the square root of n. So we should get 0.68. cool thing about using the F-size code that I just showed you is that you can check and make sure you've done stuff correctly. So there are a couple of points using ttest or this code that you can stop and go, okay, did I get the right numbers before? And everything we've done so far hasn't had that moment, I don't think, where I'm at. We're going to use our QT code. So I got 0.01 this time. So this should be a fairly big number. As alpha gets smaller, so our p less than 0.01, the numbers should get bigger. Because the smaller the percent in the tails, the further out you have to go. So the further away the cutoff score is. At 4 for my degrees of freedom. Lower tail goes false this time. So we got 3.75. So that was even bigger than any of the ones we used on the last test. The biggest we got was 2.58. Okay, here we are. So let's use ttest to come up with t. So ttest. First thing is the data set, so it's data 2 in my example. I don't remember all of them. Mu equals 2.2. Alternative, this time it's greater. And then conf dot level equals 0.01. Oop, no, I lied to you. It's 1 minus alpha, so 0.99. If you put in 0.01, it might be like the largest confidence interval ever. Or it might be the smallest one. I don't know. No. It gets larger the more confident you are. So this is going to be the smallest confidence interval ever. Okay. Let me try that. Make sure there are commas on the end of each line if you're stacking your code. So the mean of x is 3.4. That matches what I did here. Good. Okay, so my t is 1.77. Okay, my degrees of freedom matches 4. Cool. So is that going to be significant? Not even close, right? So our cutoff score is 375. Our found score is 1.77. It's not significant. And then our p-value here is 0.08. We need it to be less than 0.01. We're not doing so good. So we're going to fail to reject. Now I can go back to my calculate thing, and I'm actually going to put this, I'm going to upload the script for you guys. Well, let's just change all these out. So for my single t, I've got 3.4 compared to 2.2. Our standard deviation was 1.52. N was 5. Alpha here is 0.01. I did all that right. Let's see what happens. Okay. Let's make sure my t matches. So I got 4 degrees of freedom, 1.77. Check. Okay. My d value is 0.8 basically. That's a large effect size. So it might be that they fall in love more in the US, but we don't have enough people. So this is a power example. We clearly do not have enough of these participants to find the effect if it's there. And the two-tail confidence interval, 1 second, it's right here, 0.27 to 0.65. No, 6.53, sorry. And that includes 2.2.
Yeah. Never mind. I figured it out.
So that is a really wide confidence interval. And they're basically never falling in love, always falling in love. Yeah.
So where's the cutoff between the large, medium, and medium.
Oh, yeah, it does. I completely
When would you say,
Most people will round up. So 0.75, people kind of round up to large.
okay,
Yeah, the book does that for sure. Like 0.45, it says is medium.
okay.
It's a horrible
So, and they're just guidelines. You're not actually supposed to use them as like small, medium, and large. So this is the best idea ever. It's funny because Cohen presented those, and then later he went back and was like, I never should have done that because it depends on the research field you're working in. So like in our field, we regularly get effect sizes of like 4 and 5. So 0.8 would be really small for us. But it does help students kind of get a grasp on like when you've never seen them before, what's going on. So.